Welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on general organic chemistry, and I hope you are enjoying this course with me. Today we will be beginning with GOC part 2, lecture number 8, but make sure you watch the previous ones before being this one. In GOC part 1, we've had a detailed discussion on the nomenclature of organic compounds, and in part 2, we are discussing isomerism. The past two lectures we have been discussing geometrical isomerism, and this is going to be the last lecture on geometrical isomerism, where we are going to see a few practice problems for geometrical isomerism. This is going to be really helpful for you because you've understood the concept, but how you're going to attempt the questions, that is going to be very important, and that is what we are going to learn in this lecture. All right, and in this practice problems, I'm going to give you one trick to find the number of geometrical isomers for a compound, because this is one of the most frequently asked question in the examination. A molecular formula will be given to you, or a structure will be given to you, and you will be asked to find out the number of geometrical isomers. So for that, I'm going to give you a trick, and along with that, we are going to learn all the possible questions which are going to come in the exam, and therefore this is going to be the most helpful lecture after understanding the concept. So let us begin the learning today. So what type of questions they are asked in the examination from geometrical isomerism? Broadly, you will be seeing two type of questions. Type 1 is going to be when we have to identify in a compound if geometrical isomerism is possible or not. For example, a structure is given to you, and can you tell what is this? This is carbon number 1, 2, 3, 4, a double bonded position number 2. So this is but2ene. So you have to tell whether in but2ene geometrical isomerism is possible or not. So what are you going to do? Well, you can just see it directly, or you can just elaborate the structure, and then you have to remember the conditions which you learned previously in the past two lectures for which geometrical isomerism is possible or not. So we have three conditions. First, we should have a restricted rotation in the molecule. Then if it is going to be the carbons which are involved in the geometrical isomerism, you have to see that there should be different groups present on the carbon. And then you have to see whether those groups which are attached to the carbons, will they lie in the same plane or not. So for this structure, that is but2ene, do we have a restricted rotation? Yes, restricted rotation around the double bond is present. Next, what do we see? That we have two carbons forming the double bond. So carbon number 1, is it having different groups? Yes, it has a CH3 and a hydrogen. The other carbon of the double bond, this also has a CH3 and hydrogen. So different groups on carbon, they are present. Next, well, the groups, they should be lying in the same plane. So they do lie in the same plane. These two carbons, they are sp2 hybridized, and it is going to form all the sigma bonds in the same equatorial plane. So this is going, the groups, they will be lying in the same plane as well. Alright. So but2ene, this does show geometrical isomerism. So for any compound that is given to you, it is very essential for you to check these three conditions. If all of these three, they will be satisfied, the compound is going to show geometrical isomerism. If any one of the conditions is violated, well, the compound is not going to show geometrical isomerism, right? Now, the next type of question that can be asked to you is that you have to determine the number of geometrical isomers for a compound. So, for example, you are given how many geometrical isomers will the following compound show, and the compound given to you again. This is but2ene, right? So now you know, first of all, what you have to do again, that if such a question is given to you, first of all, you will have to check whether the compound shows geometrical isomerism or not, right? And for that, you all have seen what are the conditions, and then you will be saying that if it is showing geometrical isomerism and there is a single double bond present, then it is going to form two structures, right? So one is going to be where the two similar type of groups, they will be on one side of the double bond, and when they are on the opposite side of the double bond. So this is going to be a cis structure, this is going to be a trans structure, and for but2ene, you can draw two geometrical isomers, right? All right. Now this is very simple when you have just a single bond, there is just one bond that is present. But if there are going to be more than one double bond present, it can be 2, it can be 3, it can be 4, it can be so many. Then how are you going to find out what is the number of geometrical isomers possible for the compound? That is what we will be learning in this lecture with the help of a trick. But before that, let us see a few more questions to check whether in a compound geometrical isomerism is possible or not. Right? So we will be practicing first of all those questions where you have to identify in a compound if geometrical isomerism is possible or not. So the question that is given to us, let us see that which of the following compounds will exhibit geometrical isomerism: 2-phenyl 1-butene, 1,1-diphenyl 1-propane, 1-phenyl 2-butene, 3-phenyl 1-butene, and this was a question asked for JEE Mains 2015. Alright, so well, how are we going to proceed? Well, we will be seeing one by one all the structures, whether they will be showing geometrical isomerism or not. So the first choice is 2-phenyl 1-butene. Let us draw this in an elaborate way. So we have a double bond at position number 1, we have a phenyl group at position number 2, and we have to see whether it is going to show geometrical isomerism or not, and you have to remember the three conditions. So first of all, we have a double bond is present, so restricted rotation about the double bond is possible, right? The next we have to see that whether we have different groups on the carbon of the double bond. So here you can see that on this carbon we have a ethyl group and we have a phenyl group. So these two groups, they are different. But on the other carbon, well, we have two hydrogens. Two hydrogens means we have same groups on the carbon. Therefore, well, this structure is not going to show geometrical isomerism. Right? So you have to check all the three conditions, starting from restricted rotation about the double bond, or if it is going to be a ring structure, well, it is going to be a restricted rotation. So you have to see whether a restricted rotation is present or not. And then we have to see that the different groups are present. If they are also present, then you will be moving on to the next. So one by one, we will be checking all the three conditions, right? So the next structure we have is 1,1-diphenyl 1-propane. So we have propane 3 carbons, and at position number 1 we have 2 phenyl groups. So we've drawn the structure. Again, you have checked the three conditions. So we have the first condition, that is restricted rotation. Can we see any restricted rotation over here? Well, we cannot. So this means that this condition is not satisfied. We do not have to move further. Well, this compound is also not going to show geometrical isomerism, right? So moving on to the third choice, we have 1-phenyl 2-butene. So again, let us draw the structure for it. We have a double bond at position number 2, we have a phenyl group at position number 1, and we have the three conditions with us. So restricted rotation about the double bond is possible. So first condition is satisfied. The next, we are supposed to have different groups. So here what you can see is that we have a carbon-carbon double bond. At this carbon, well, we have one carbon and the other is going to be a hydrogen, right? And the next carbon, what will we have? Well, we will be having, it is forming a double bond this side and it is a single bond this side. So this is going to be a carbon, and here you will be having a hydrogen. Do I draw that? Well, so this is going to be a hydrogen over here and a hydrogen over here to satisfy all the four valencies. So what you can see is that this carbon is attached to a carbon and a hydrogen, and this carbon is also attached to a carbon and a hydrogen. So this means that there are going to be different groups present, right? So the second condition is also going to be satisfied. So this is also correct, and well, these groups, they will be lying in the same plane. The two carbons, they are sp2 hybridized. It is going to be all the sigma bonds on the equatorial plane. So the third condition is also satisfied, and as all the three conditions, they are satisfied, so this compound is going to show geometrical isomerism. So if it is a single correct choice, you have got the answer as the C choice just now also. But let us see the fourth choice as well. So here we have 3-phenyl 1-butene. So again, we draw the structure. So what you can see is that we have a double bond at position number 1 and a phenyl group at position number 3. Again, the three conditions for us. So we can have a double bond a restricted rotation is present. Different groups, again you can see that this carbon is attached to two hydrogens, so they are not different groups on the carbon. So structure number D is also not going to show geometrical isomerism. So the correct option over here is going to be C choice. Now let us see another question, and again we have to find out which of the following compounds is going to show geometrical isomerism or not. So here the choices are A, B, C and D. So let us do this now orally. We are not going to write the conditions, but we are going to just mentally check them, because in the examination you are not just going to write those conditions on the piece of paper. You have to write it on your mind only, right? So we have first choice. So here what you can see is that we have a cyclic structure and a cyclic structure with a double bond. So this is going to be a cycloalkene. What is this going to be? This is a 5 carbon ring. So this is going to be cyclopentene. Now in this cyclopentene, well, do we have a restricted rotation? Yes, we have a double bond. So there is a restricted rotation present. And the double bond, can we see different carbon, different groups attached? Well, we can see there is going to be a hydrogen here, and this is a carbon. So for this carbon, we do have different groups, a hydrogen and a carbon. Similarly, for this carbon also we will be having a hydrogen, and this is going to be a carbon. So again, for this also we have different groups as well. Are they going to be lying in the same plane? Yes, they will be lying in the same plane as well. But now, this all conditions being satisfied, still this compound does not show geometrical isomerism. So here you have to remember what are the things that we have learned apart from these conditions. Well, what we have learned is that when we have a cycloalkene which is having 7 or less than 7 members, well, we can draw the cis and the trans on a piece of paper, but actually it is not possible, because for these rings, well, there's going to be a lot of strain for the trans structure. So we can draw only the cis structure for this, and therefore this is not going to show geometrical isomerism. But when you move on to choice B, what you can see is that, well, if you're going to count them, this is going to be a 10-member ring, right? So this is cyclodecene. And in cyclodecene, what you can see is that again there is a double bond present. So again, all the conditions will be satisfied here, and because this ring has more than 7 members, so we will be able to see a cis and a trans for this structure. So for B, geometrical isomerism is going to be possible. Next, we move on to C. So we can see a double bond, restricted rotation is present. Again, then we have to say different groups. So here you can see that this carbon, this is attached to two hydrogen. So same groups on the carbon, the geometrical isomerism is not going to be shown. And then for D, what you can see is that this carbon of the double bond is attached to CH3CH3. So again, same methyl groups attached to this carbon. So this will also not show GIC. So the correct option is going to be B choice. I hope this is clear. Please do remember, for cycloalkenes, the rings with more than 7 members is only going to show geometrical isomerism. So these are the things that you have learned as special cases in the last lecture, right? So this is how you're going to apply them as well. So now that you know how to identify for a particular compound whether geometrical isomerism is possible or not, let us see how we are going to determine the number of geometrical isomers for a particular formula. So the question we have is, how many geometrical isomers will this structure have? Alright, so here what you can see is that we have two double bonds present in this compound. Right? If it would have been one double bond and the compound was satisfying all the conditions of geometrical isomerism, well, we would have drawn two structures. One would be a cis, and then we would have a trans. But now we have two double bonds. How are we going to proceed? So first of all, you should be able to identify whether both of these double bonds we will be having geometrical isomerism or not. Alright. So the first condition, a restricted rotation, a double bond is present. So restricted rotation is present. Then they should be having, say, different groups attached to the carbon. So if this is the carbon, one attachment is a hydrogen and the other is a carbon. Similarly, for this one attachment is a hydrogen and the other is a carbon. Different groups. So this is also possible, and because these are no any special conditions that you have learned in the previous lecture, so these all they are going to be in one plane only. All right. The next what you have is this carbon carbon double bond. So here also you can see that the carbon is attached to a hydrogen and a carbon, a hydrogen and a carbon. So again different groups attached. So both of the double bonds they will be showing geometrical isomerism. So this is very essential for you first of all to check whether the double bonds they are showing geometrical isomerism or not. Alright. Now the next step is going to be write the possible structures. So if you consider this to be the expanded way how we have written it, so you can see over here starting from this side it is the C2H5. We have a carbon carbon double bond. So on this carbon we have a hydrogen, so we've drawn that. The next carbon we have a hydrogen, and the next we had a carbon carbon double bond. So for this carbon carbon double bond, one hydrogen and CH3. So this is the expanded way which we can write. So here first of all what we have drawn is that for both of the two carbons double bonds we will be having a cis and a trans possible. Alright. So this can also show a cis and a trans. This can also show a cis and a trans. So when we are drawing that what you can see is that for this carbon carbon double bond this one. Alright. So we have C2H5 on this side of the carbon bond and the carbon also, and the two hydrogens they are on the same side of the carbon carbon double bond. So this is going to be a cis, and for the next one what you can see is the hydrogens they are opposite each other, so this is a trans. The next what you can see is the hydrogens they are on the same side. The next hydrogens they are on the same side, so this is a cis structure. All right. The next what you can see is now we have the two hydrogens on opposite side for this one, so this is a trans, and again the next we have hydrogens on the two sides, so this is also a trans. All right, I hope you can identify these things now. Hydrogen on opposite side of the double bond, so a trans. A hydrogen on opposite sorry the same side, so this is going to be a cis. So a cis trans, a cis cis, a trans trans and trans cis structures they are possible because we have two double bonds around which geometrical isomerism is possible, and for both of them you can draw a cis and a trans. So the number of geometrical isomers for this compound is going to be 4. Alright, I hope this is clear. So let us see one more question now. So now in this again question you are given a structure and you have to tell how many geometrical isomers they are going to be possible. So again you can see in the structure there are two double bonds, so you have to first of all check whether this is going to satisfy the conditions for geometrical isomerism and when it is going to. Alright, so we have carbon carbon double bond restricted rotation, and around both of the double bonds we have different groups attached and they are going to all lie in the same plane as well. So we have two double bonds. Again you can draw the cis and trans for both of them. Let us do that again. Alright, so when you're going to draw the expanded notation you can see the hydrogens on the same side, hydrogens on the same side, so this is a cis cis structure. Then for the next what you can see is that we have made the trans one. So hydrogens on opposite side, hydrogens on opposite. So this is a trans trans structure, right? The next what you can see is that we have kept this to be the cis and the other we have made a trans. So this is a cis and a trans. And for the next again what we have done is now we have made a trans for this and a cis for this. So this is a trans and a cis. Again 4 geometrical isomers possible? Well, no, not this time. Why not this time? Because what you can see is that this structure, this is a symmetrical structure. Alright. The previous one, I'll just come back to that again. But that was an unsymmetrical structure. Here we had a CH3 and the other side we had a C2H5. Alright. But what you have in this structure is that on both ends you have a C2H5. So if you compare from both the ends, here we have a CH25, here we have a CH25. The next is a single bond, a carbon-carbon double bond, a carbon-carbon double bond, and then a single bond. So you can divide this structure over here into two identical halves. So this is a symmetrical structure. Alright. So now if you start from this as carbon number 1, carbon number 2, carbon number 3, carbon number 4, 5, 6, 7 and 8. Alright. And the other way is that you start the numbering from the other side. Just look at this. So this is 1, 2, 3, 4, 5, 6, 7 and 8. Alright. So this is octadiene where we have at position number 3 and position number 5 a double bond. Right. So this is 3, 5 octadiene. Similarly, if you start the numbering from this side, you will be seeing that this is also 3 and 5 octadiene. So both of them you can start the numbering from from either of the ends, right? So when you're starting the numbering from this side, this is a cis and a trans. If you start the numbering from this side, this is a cis and a trans. So essentially these two structures, they are identically the same. It is only what you are seeing is that we have just a numbered from, if you are numbering from this side, this is a cis and a trans, and this is a trans and a cis. But if you see from this side, this is also a cis and a trans, and both being symmetrical structures, so well this is going to be the same. So the number of geometrical isomers which are possible for octa 3,5-diene, well this is going to be 3 possible geometrical structures. Alright, so here now I'm going to give you a trick where you will be able to tell whether if we have a symmetrical structure or an unsymmetrical structure. We have this many number of double bonds, we have this many number of double bonds, and you can just quickly write with the help of a formula how many possible geometrical isomers the compound is going to have. So let us see now that trick. So the trick to find the number of geometrical isomers, please proceed for every compound the way I am teaching you. Alright. So the step 1 is that you have to find the number of stereogenic centers in a compound. Now what is the stereogenic center? Well, this is going to be that carbon where the interchange of two groups converts a cis isomer into a trans isomer. Let me explain you with the help of the examples that we've just now seen. So the first example was 2,4-heptadiene. We did not write down the name there. So this was the structure that you saw for which 4 geometrical isomers were possible. Right? If you name this compound, this will be carbon number 1, 2, 3, 4, 5, 6 and 7. So heptadiene. It is position number 2 and position number 4 for the double bond. So 2,4-heptadiene. Alright, so here what you can see is that we have two double bonds where geometrical isomerism is possible. If you take hold of this carbon with its group and just change the position of the groups attached to the next carbon, what you will be seeing is that you will be able to convert a cis into a trans, and if it is a trans, you will be able to convert the trans into a cis. So here a cis gets converted into trans, so this is stereogenic center number 1. And the next also you saw that there were different groups attached, so here also geometrical isomerism is possible. You can convert a cis into a trans into a cis, right? So this is stereogenic center number 2, where we can interchange the position of the two groups to convert a cis into a trans. I hope this is clear. And where therefore, when you have two stereogenic center, what did you do? A cis and a trans for this and a cis and a trans for this, and the combination that gave you 4 geometrical isomers, right? The next what you saw was 3,5-octadiene, right? So this we named also the compound, so I hope this is clear. So this is 3,5-octadiene, and here also we have two double bonds where geometrical isomerism is possible. So this is also meaning that we have two stereogenic centers. Now why we are focusing on identifying two stereogenic centers and just not simply seeing that we have two double bonds? Well, if we have a double bond and we have the carbon attached to it, for example, this is a CH2 group. So a CH2 group with a double bond, well, that will not show geometrical isomerism. So it is very essential for you to identify wherever you are thinking that geometrical isomerism is going to be possible, just check the conditions for geometrical isomerism. If they are being satisfied, well, that is going to be a stereogenic center. Alright, if you do it this way, you will never get your question wrong. Now, what you saw was that we identify in both of the structures that we had two stereogenic centers, but for 2,4-heptadiene 4 isomers and for this 3 isomers. So how are we going to develop a trick to find the number of geometrical isomers? Well, the next step is going to be that you have to identify whether the compound is symmetrical or not. If the compound is unsymmetrical, then the number of geometrical isomers possible for that compound is going to be 2 to the power x, where x is the number of stereocenters. For example, if you look at 2,4-heptadiene, right? So this is an unsymmetrical compound. We start with the double bonded position number 2 from this end, and from this end it is going to be double bonded position number 3. So this is an unsymmetrical molecule. If you divide it from the center, well, you are going to see different halves. They are not going to be the same. So it is unsymmetrical. So 2,4-heptadiene is unsymmetrical and the value of x is going to be 2 because this has two stereocenters. So 2 to the power 2 is going to give you 4 stereoisomers. So this is what you had drawn also, right? But now with this formula, well, you do not have to draw all the possible stereoisomers. You have just identified what are the stereocenters. This is an unsymmetrical molecule and you have put up the formula 2 to the power x for an unsymmetrical molecule and you get this 2 to the power 2 as 4, right? Now, the next we had was 3,5-octadiene. So in this, what do we have? Well, this is a symmetrical molecule. You've already seen that, right? So for a symmetrical molecule, the number of GI, we have a different formula. This is 2 to the power x minus 1 plus 2 to the power y minus 1. Now, x you already know that this is the number of stereocenters in the compound. Now, what is y? Well, y is going to be x divided by 2 if x is even. If the number of stereocenters is even, then you are going to divide the number of stereocenters by 2 to give you the value of y. But if the number of stereocenters, the number is an odd number, it is 3, 5 and so on, then what you will be doing is x plus 1 divided by 2, this will give you y. Alright. Now, for 3,5-octadiene, you know that this is a symmetrical molecule. Symmetrical molecule, it has two stereocenters, so this is even. So you have to find out x is 2, you have to find out the value of y. Y is going to be x divided by 2. So 2 divided by 2, the value of y will come as 1. And then we will be putting these values in the formula 2x minus 1 plus 2 to the power y minus 1. Right? So what you will be getting is 2 to the power 2 minus 1. So this is going to be 2 to the power 1 and the next it is going to be 2y minus 1. So 1 minus 1, this will be 0. So this is going to be 2 plus 1. This is going to be equal to 3. Right? I hope this is clear to you people how we have done this. So this is going to be equal to 3. So when we had 2,4-heptadiene, we got 4 and when we had 3,5-octadiene, we got 3. But now we do not have to draw the structures. We do not have to compare each and every structure whether it is same or not. We can just simply apply a formula and get our answer. Right? I think it is easy enough, not at all difficult. Just you have to remember the formula, yes, for sure. So now that we know the trick, let us use the trick and do a few questions. So the first question is, how many geometrical isomers does this compound have? And what you can see is that this compound, this has 3 double bonds. 3 double bonds. Well, if all of them they are going to show geometrical isomerism, you will have to draw all the possible cis and trans combinations, right? And then check also whether they either of them is going to be same or not and then cancelling them out. Well, this is going to take hell lot of a time if you do not know the trick. But now that you know, we are going to just use that trick only and find out our answer, because in your examination, well, you're not going to have that much of a time to draw all the possible structures. right? So we have the trick, and in the trick what you have to do, first of all you have to find out what are the number of stereogenic centers. So if you look at this compound, you will be able to identify that all of the three double bonds, they are different groups attached, so all of them, they are going to be stereogenic centers. Alright, so we have three stereogenic centers over here. The next you have to see whether the compound this is symmetrical or not, and what we find is that this compound is symmetrical. How do you check that it is symmetrical? Well, what you can do is start from both the ends, keep on comparing them, right? So we have a CH3, a CH3, a CH, a CH, a double bond, a double bond, a CH, a CH, again a CH and a CH. So you will be able to divide this compound into two halves if you divide it at the double bond. Alright, so this is going to be identical to halves. So this is a symmetrical compound. And what is the formula that we have learned for a symmetrical compound? Well, for a symmetrical compound, the number of Gi is going to be 2 to the power x minus 1 plus 2 to the power y minus 1. Right? And what is going to be x? It is going to be the number of stereogenic centers. And what is going to be y? Well, y is going to be, well, for this compound, x is 3. So that is an odd number. So that is going to be x plus 1 divided by 2. So what you will be getting is x is 3 and y, which is x plus 1 divided by 2. So this is going to be 3 plus 1, 4 divided by 2. So this comes up to 2. So x is 3, y is 2. Put the values into the formula, and what you will be getting is, well, this is going to be 6. Alright, so just solve this and you will be getting the number of geometrical isomers possible for the compound. This is going to be 6. Easy enough. I hope this is not at all difficult. Great. So finally, what you're going to write as the answer, you can be given a multiple choice question also possible, 3, 4, 5, 6 structures possible. So it is going to be 6 geometrical isomers for this compound. Finding out the number of stereogenic centers and then finding out whether the compound is symmetrical or not and using the formula appropriately. Perfectly fine. Well, doing a structure on 2,4-heptadiene, well, this gave me a remembrance that we have to see one more type of question. And the question is, what is the IUPAC name for the following compound? So this is 2,4-heptadiene, but well, the choices that were given to you now are these. This means what? Well, this is a 2Z and a 4Z, 2,4-heptadiene, a 2Z, a 4E, a 2E, a 4E, a 2E, and a 4Z. So what is this structure that is given to us? I hope you all remember the EZ system of nomenclature that we did in lecture number 1 of geometrical isomerism. So here what are you going to do? Well, what you're going to see is which is the group of priority around the double bond. So we will be starting with this as carbon number 1, carbon number 2, 3, 4, 5, 6 and 7. So carbon number 2, what you can see is a double bond present. To this carbon we have a CH3 and a H. So this is going to be the group of priority. And from the other carbon, well, this is going to be the group of priority, the next carbon that is attached, right? So we have this to be the group of priority, and here the atomic number criteria says that carbon is going to be more of a priority than hydrogen because it has a higher atomic number. Now these two groups, you can see they are on the opposite side of the double bond. So this is going to be what? It is going to be an E. Alright, and in the next what you can see is that we have this to be the stereogenic center, carbon-carbon double bond. Here what you can see is that this is going to be the group of high priority, and on the other side this is going to be the group of high priority, and they are both on the same side of the double bond. So this is going to be a Z, a E and a Z. E at position number 2 and a Z at position number 4. So this is going to be 2E4Z, 2,4-heptadiene. And you can also write this as a cis and a trans also. A E is similar to a trans and a Z is similar to a cis. So this is a trans cis 2,4-heptadiene. So this is also one way that the choices they can be given to you. So the correct option is going to be D choice. So this is another type that can be asked in the examination based on the learning that we have done. Now let us see a varied mixed bag of questions and how you are going to attempt them, all that you have learned in geometrical isomerism. Alright. So the question we have now is that how many geometrical isomers they are possible for this compound, and what is the name of this compound? Well, it is going to be 1,2,3 trichloropropane. Now before we can tell how many geometrical isomers, we have to tell whether geometrical isomerism is possible also or not for this compound. Right. So what is essential? Well, we all know that molecule should have restricted rotation, and well, this molecule shows restricted rotation because of the presence of a ring. So you all know, just like a double bond, the ring also gives a restricted rotation. If we hold one carbon and try to move the other carbon, well, we are not able to, because this is bound on two sides by the two carbons, and the next one is also bound back to the next carbon. So all of them, they are bound to each other in such a tight way. Well, we have a restricted rotation. Now restricted rotation, and if we have two of the carbons of the ring having different groups, well, this is going to show geometrical isomerism. All right. Now if you look at this carbon, well, this is forming two bonds with the two carbons of the ring, and it is going to have two valencies. One of it is showing with a chlorine atom, and the other is going to be the hydrogen atom. Right. So we will be having a hydrogen over here. We will be having a hydrogen over here. And similarly, we will be having a hydrogen over here as well. Clear, I hope. So what this means is that this carbon, well, this is having two different groups, this is also having two different groups, and this is also having two different groups. So we will be able to have geometrical isomerism for 1,2,3 trichloropropane. So let us draw the structures which are possible. So the first structure I draw is when all the three chlorine atoms, they are pointing towards us, which is shown by the wedge representation. And the other structure possible is when the three chlorines, they are going back behind the plane of the ring, and this is represented by the dash projection. Right. The other structure which is possible is, well, I can keep one of them to be a wedge. All right, and I'm making two other to be dash. One is coming towards us, and two are going back. And similarly, another representation which we can draw is when two of them, they are coming towards us and one is going back. So these are all the possible combinations that we can have. Now if you look at both of them, well, you will be finding them to be the same. Why same? Because we will be comparing the two chlorine the carbons. So this over here, the two carbons, well, they are in a cis position because both the chlorine atoms, they are on one side of the ring. Similarly, if you look at this, well, again, this is a cis representation because both the chlorine atoms, they are coming out. Right. And similarly, this one is also a cis because both the chlorine atoms, they are coming out. Okay. So similarly, if you look over here, well, we will be having a cis because both the chlorine atoms, they are going behind the plane of the ring. Here also, both of them, they are going behind the plane of the ring, and here also they are going behind the plane of the ring. So this is also a cis representation for all the atoms, and this is also a cis representation. So it is just like looking from the two sides, the same structure, one from the front and one from the back. So we are going to have this as only one isomer. Now the next, let us see this one. So here we have a wedge and a dash. So this is going to be a trans. This is a dash and a dash. So this is going to be a cis, and this is a wedge and a dash. So this is going to be a trans. Let us look at this one. So this is a a wedge and a wedge. So this is going to be a cis. A wedge and a dash, it is going to be a trans, and here it is also going to be a trans, a wedge and a dash. All right. So here what you can see is two trans and one cis, and here also two trans and one cis. So these two structures also, they are identical. All right. So they will also be the same, and therefore we will be having only two geometrical isomers possible for this compound. I hope now this is clear to you how you are going to ascertain whether the compound is going to form how many geometrical isomers in such a question. So you can have a cyclobutane, you can have a cyclopentane, you can have a cyclohexane. So you should be able to do the questions just like we have done over here. Fine. All right. So now let us see the next question. How many geometrical isomers they are possible for this structure? Well, when you are going to count the number of carbon, this is going to be 7 carbons. It will be carbon number 2, carbon number 3 and carbon number 5, which will be having a double bond. So it is going to be 2, 3, 5 heptatriene as far as the name of this compound is concerned. And we have to find out how many geometrical isomers they are possible. So the first step is going to be finding the number of stereo centers for this compound, right? So if you look at this carbon-carbon double bond, so this is going to be 1 point of restricted rotation. If you look at the 2 carbons which are going to be attached to it, so this is the carbon number 1. So this will be attached to a hydrogen and a CH3. So different groups. For this carbon, it is going to be a hydrogen and a CH. So again, different groups. So this is going to be one of the stereo centers. Now let us look at the next one. If you look over here, just let me rub the other part of it. Right now, if we see over here, what you can see is that we have consecutive double bond. Now what do we call a consecutive double bond? Well, we call it as a allene. I hope you all remember that we discussed about the allenes in the last lecture. And in an allene, what did we learn? What we learned was that the two double bonds, well, they are going to be in a different plane. If one of them is going to be an xy plane, the other one will be in a yz plane, and therefore the atoms which are going to be attached to the two carbons at the terminal positions, well, they will be in a different plane. All right, I hope you all remember. So this is what we have: a C, a double bond C, a double bond C. Okay, so here one of it is going to be a H and the other is going to be a CH, etc., etc., whatever is on this side. And then we have a H and a CH3. So we have double bond, we have a restricted rotation, we have different groups attached to the two terminal carbons, right? So it seems to be that it is going to show geometrical isomerism, but this is going to be in one plane and this is going to be in another plane. And when they are in another plane, I have already told you, when the groups they are in a different plane, well, that structure is not going to show geometrical isomerism. So for this portion of the double bonds where you are seeing that there are double bond present, this is a restricted rotation, different groups also attached, but this portion will not be showing geometrical isomerism. The only portion where geometrical isomerism is possible is this carbon-carbon double bond, right? So this one with a star over here. So it is going to have just one stereogenic center, and when it is going to be one stereogenic center, it is going to be 2 to the power 1. That is going to be 2 isomers possible. 2 geometrical isomers possible, right? I hope it is clear to you. In case you have not watched the previous lecture where we did discuss about the allenes, please do watch that for a thorough understanding of the concept. Right, now let us see the next question. So the next question we have again a structure where now you can see that we have 3 consecutive double bonds and then we have one more double bond. All right, so here what is going to happen? Well, this has an odd number of consecutive double bonds. These are 3. Okay, and when it has odd number of consecutive bonds, the molecule is going to show Gi, as the group of atoms now they will be in one plane. Okay, so if this one is going to be in the xy plane, this will be in the yz plane, and this will be in the xy plane. So these ends over here, right, these will be having the atoms attached to them in the same plane. So if these atoms attached to them, they are different kind, well, this as one unit will be one stereo center. Okay, I hope this is clear, and this will be the other stereo center. So as total, we will be having 2 stereo centers. Let me just elaborate the consecutive 3 bonds so that is clear to you. So we are having this over here. So this will be one H and a CH and a double bond, etc., etc., whatever is on this side. And here we have, we will not write the H over here, so we will be writing a H and a CH3. So this in total, this is behaving as one continuous double bond, you can say. And you can say that these carbons at the end of this big continuous double bond, well, this is having a hydrogen and a CH3 different groups, and this is having different groups, and now they are in one plane. And because they are in one plane, well, this is going to show geometrical isomerism as one unit. All right, it is not going to be three double bonds, three structures that are going to show different geometrical isomerism. They are going to behave as one stereogenic center. All right, and the next is the other double bond. So in total we will be having two stereogenic centers, and because the molecule is an unsymmetrical molecule, so it is going to be 2 to the power 2. Therefore 4 geometrical isomers they are possible for this compound. All right, so please do remember this. This is very important. Now, when we have three consecutive bonds, so it is going to be, well, odd number of bonds. If we have even number of cumulative double bonds or consecutive double bonds, there is going to be no GI. And when it is going to be odd number of cumulative double bonds in the molecule, geometrical isomerism will be possible, as you have seen over here. All right, just like we have for the double bond, when we have two of them together, so it will be in the xy plane, a yz plane. If we have the next one, it is going to be in the xy plane, and in the next one it will be again in the yz plane. So the two ends in a even number of cumulative double bonds, well, they will be in different planes, so no geometrical isomerism. And when we have odd number of cumulative double bonds, we say that it will be showing geometrical isomerism, and it will be behaving as one stereo center. All right, now when the cumulative double bond structures, they are called as cumulanes. So do remember this. When we have two double bonds together, we call this as an alene. When we have a hydrocarbon with three or more than three cumulative double bonds or consecutive bonds, we call it as a cumulane. All right, I hope you will remember this added information, but a very important one. Now the next question, how many geometrical isomers they are possible for cis structure? Now what is this? Well, this is a spirocyclic compound, and similar to the allenes and the cumulanes are going to be the spirocyclic compounds. We learned it in the last lecture as well. Right? So if this ring is going to be in the xy plane, the next is going to be in the yz plane, and this will be again in the xy plane. So the groups, if they are different at the two ends of the rings, well, if they are different, well, this is going to show geometrical isomerism, because now they are again in the same plane. Rings, restricted rotation, all right, two different groups at the terminal positions, and because they are in the same plane, so geometrical isomerism is possible for this compound. So it has an odd number of spiro rings. The molecule will be showing geometrical isomerism, and it will be behaving as one stereo center. So it is going to be 2 to the power 1. So it will be having two isomers, two geometrical isomers. One is going to be a cis, where we have the two CH3 on same side, and the other is going to be a trans, when the CH3s they will be on opposite side. All right. So even number of spiro rings in a molecule, no GI will be possible. Odd number of spiro rings in a molecule, GI will be possible. If there was an additional ring over here, so it would be in the XY plane, a YZ plane, a XY plane, and a YZ. So YZ and XY again different planes, so no GI possible. So this is something that you have to remember for the allenes, the cumulanes, and the spiro rings, just the same way. So two geometrical isomers, they are possible for this compound. Let us see one more question. How many geometrical isomers they are possible for this structure over here? Alright, so in the structure what you can see is that one, we have a cyclohexane ring, and to this we have a substituent where we have double bonds. Okay, so let us see now where all geometrical isomerism is possible. You all know that when we have a cycloalkane, well, that is going to be a structure where we can have a restricted rotation. All the carbons, they are sp3, and if we have two sp3 carbons of the ring, well, having different groups attached to it, well, this is going to be a place where geometrical isomerism is possible, right? So here what you can see is this part of the ring where we have Okay, so this is going to be the carbon. To this carbon and this carbon, well, this is going to be one group for both, and this is going to be the other group for both. All right, so both groups, they are different for the two carbons of this ring. So we will be having one stereogenic center at this place, and the other stereogenic center, let us see whether the double bond, well, this can also show geometrical isomerism or not, right? But what you can see is across the double bond, this carbon is having two hydrogens. This is also having two hydrogens. So the carbon of the carbon-carbon double bond, well, this is having same groups on one side. So this will not be showing geometrical isomerism. This will also not be showing geometrical isomerism. So we have just one stereogenic center for this structure. All right. And that is going to be the cycloalkane ring. So X is going to be 1, and the number of geometrical isomers possible for the structure, they are going to be again 2 to the power 1, that is 2. So let us see now a modified of this question. So what we have done over here is that instead of a CH2, now we have put a CHBr. So along with the stereo center, which was of the cyclohexane ring, now we have one more stereo center, this double bond of the substituent side chain, right? So we have at this position, we will be having one carbon and other will be a hydrogen, and on this side we will be having a hydrogen and a bromine. So we have two stereo centers for this compound, and because this is an unsymmetrical structure, so the number of GIs will be 2 to the power 2, that is 4. All right, I hope this is clear. The things, they should now be very clear to you people. So 4 isomers, they are possible for this structure. So now this is going to be the last question for today. How many geometrical isomers they are possible for this structure? So I would like you all to pause and find the answer yourself and then look at the solution. Now, if you've done that, well, we will be just now seeing the solution. But before that, I would just like to share with you that here I have taken various possible questions which can be asked in the examination. The other option for me was to take up the questions which had been coming in the previous year examination, like the JEE Mains 2015 question that I showed you as one of the questions today. But well, we will be doing that also, but once we are finished with the whole of isomerism. And that is actually the best time to look at previous year questions when we have had a clear understanding of the whole concept. All right. And that becomes a test for us how much we have gained from our learning when we look up at the previous year questions. All right. So for this structure, well, we have a cyclohexene ring. Cyclohexene ring, first of all, if we have this as a double bond, you all know that we have a 6-membered cycloalkane ring. So this double bond, this will not be showing geometrical isomerism. All right, it is going to be only 8 and above 8 ring when we can have this alkene to be showing a cis and a trans. Before that, it is always a cis. So no choice over here. The rest of the carbons of the ring, well, you can check wherever we have sp3 hybridized carbons, that whether if there are two different groups attached to the carbon and we have two of them. If we have two of them, well, they also can be one of the stereogenic center. But in the structure, what you will be seeing is that it is only at this one point where we are having two different groups attached to the sp3 hybridized carbons. Okay, so this also, the all of the rest 4 of the carbons, well, they will also not be showing geometrical isomerism. Now we move on to this double bond. So where geometrical isomerism is possible or not. So here what you can see is a carbon-carbon double bond. This is attached to one carbon, so the next fourth valency is going to be a hydrogen. Similarly, this one is attached to a methyl group. So again, the last valency, the fourth valency is going to be a hydrogen. So this carbon-carbon double bond, this has the 2 carbons attached to different groups. So this is going to be the one where we will be seeing one stereo center, and X is 1. Therefore, the number of GIs possible is going to be 2. Cis and a trans. All right, so 2 geometrical isomers. So I hope now the whole concept, this is clear to you. Practice a lot many questions, and if you face any difficulty, please share them with us. We will be helping you the maximum possible. So that would be all for this lecture. I hope you've enjoyed the lecture, you have understood everything, and now with the whole concept understood in the past two lectures and how to attempt the questions you have learned in this lecture, there's going to be no single question that is going to come in the examination that you will not be able to attempt. So that is what we are aiming for, your best possible attempt in the examination. And the next lecture, well, we will be starting the discussion on optical isomerism. Again, a very important concept, and the students consider this to be very difficult. But we try our level best to make it your best one. So see you again. Have a nice day. God bless you.